Hello and welcome. Settle in wherever you are. Maybe you are lying in a quiet room with the lights low and the world outside going about its business without you. Maybe the ceiling above you is familiar, close, and small. That is good. Hold on to that feeling of smallness, because tonight we are going to need it. Take a moment before we begin to notice where your body is. Notice the surface beneath you, whether it is soft or firm, warm or cool. Notice the weight of your limbs, the gentle rise and fall of your chest. Notice the sounds around you, whatever they are, and let them recede, the way background noise recedes when you stop paying attention to it. You do not need to do anything with those sounds. You do not need to silence them. Just let them be there, in the background, while something larger comes to the foreground. My name does not matter. What matters is what I am about to tell you. And I want you to understand, before we begin, that everything I am going to describe to you is real. It is not a metaphor. It is not a story. It is a structure, a physical, measurable, colossal structure, hanging in the universe above us right now, at this very moment, as you breathe and blink and feel the weight of your body against whatever surface is holding you. It exists, and the fact that it exists is one of the most unsettling, most beautiful, most deeply strange things that science has ever uncovered. So take a slow breath, let your shoulders drop, and let us begin at the beginning, which, in this case, means beginning with something familiar before we walk together into something that is anything but. Think about your bedroom. The walls, the floor, the ceiling. Picture the dimensions of that room in your mind. Maybe it is 4 meters across, maybe 5. It is a space you know by feel, by memory. You could walk it in the dark without bumping into a single thing. That room, that small, known, comfortable space, is your starting point tonight. Now step outside of it. Step outside of your house, or your apartment, or wherever you are. Imagine standing in the street, looking up. The sky above you is the same sky it has always been. But tonight, we are going to follow it upward. Not just to the clouds, not just to the stars, but all the way to the very edge of what the human mind has ever dared to measure. And so we begin with a comparison. A slow, deliberate, step-by-step comparison, because the only way to approach what we are going to talk about tonight is carefully. If you rush at it, your mind will simply refuse. It will hand the number back to you, unprocessed, like a word in a language you have never studied. So we go slowly. We build the scale the way you build a staircase, one step at a time, each one resting on the one before it. Step 1. The Earth. The Earth is, by any human measure, enormous. It is about 12,700 kilometers across. If you try to drive around the equator in a car without stopping, it would take you more than 16 days. 16 days of continuous driving through every time zone, across every ocean, to complete a single loop around the surface of our planet. That is a large thing. That is a genuinely, impressively large thing. And for almost the entirety of human history, it was the largest thing most people ever needed to think about. Imagine, for a moment, that you are looking at the Earth from space. Not as an abstract image on a screen, but as though you are actually there, floating in the dark, weightless, looking down at the blue and white sphere below you. The oceans catch the light of the sun and scatter it. The clouds swirl in great arcs, following patterns that have nothing to do with the borders humans have drawn. The continents are brown and green beneath the cloud cover, familiar in their shapes but strange in their silence. There is no sound in space. The Earth turns without noise. It has been turning for 4.5 billion years without making a sound that anyone outside of it could hear. It is, in the silence of the cosmos, a beautiful and quiet thing. But hold the Earth in your mind for a moment. not as a map or a globe, but as a single object suspended in space. A sphere, blue and white and brown, floating quietly in the dark. It is beautiful, but it is also, against what comes next, vanishingly small. Step 2. The distance to the Sun. The Sun is about 150 million kilometers away from Earth. That number sounds large, but let us make it physical. If you could travel at the speed of a commercial airplane, moving without stop at roughly 900 kilometers per hour, it would take you about 19 years to reach the Sun. 19 years of flying through empty space, with nothing to see, to cover the distance between our planet and its star. That is the first real sense of astronomical distance, not the distance to the Moon, which is large but still imaginable, but the distance to the Sun, which already begins to strain the mind. Picture that flight for a moment. Not the destination, the journey. 19 years of moving through darkness at the speed of a passenger jet, with the Sun growing imperceptibly brighter day after day, year after year, until finally, after nearly 2 decades of continuous travel, you arrive at the surface of a star. A star that is so hot that the concept of a surface barely applies. A churning, erupting, magnetic, million-degree ball of plasma, 8 minutes of light travel from the planet where you were born. But the Sun itself, how large is it? The Sun is about 109 times wider than the Earth. If the Earth were the size of a marble, the Sun would be the size of a large beach ball sitting several meters away. It is, by any measure we use in daily life, colossal. But step 3 is where things begin to change. Step 3. The solar system. The solar system extends far beyond the Sun and Earth. The outermost planet we formally recognize, Neptune, orbits the Sun at a distance of about 4.5 billion kilometers. That is 30 times farther from the Sun than the Earth is. If our earlier 19-year airplane flight got us to the Sun, then reaching Neptune from Earth would take nearly 570 years. More than 5 centuries of flight, in a straight line, through darkness. Neptune is a blue world, deep, cold, blue, with winds that move faster than the speed of sound on Earth. It has moons, one of which, Triton, orbits in the wrong direction, suggesting it was captured from somewhere else, from outside the solar system, long ago. And Neptune is itself just one of 8 planets, dozens of moons, millions of asteroids, and billions of comets that make up the solar system. All of it, all of that complexity, all of those worlds, contained within a sphere 4.5 billion kilometers across. And even that is not the true edge of the solar system. The Oort cloud, a vast shell of icy bodies thought to surround our solar system, extends perhaps 1.5 light years from the Sun. That is the first time tonight that we use the phrase light year. And we need to pause here, because from this point forward, the unit of measurement we use will always be light years, and the numbers attached to those light years will keep growing in ways that feel almost violent. A light year is the distance that light travels in a single year. Light moves at nearly 300,000 kilometers per second. In 1 second, light could travel around the Earth 7.5 times. In 8 minutes, it reaches the Sun from Earth. In 1 year, 365 days of that same speed, maintained without interruption, light covers approximately 9.5 trillion kilometers. That is a light year. 9.5 trillion kilometers. 1. Light. Year. Sit with that for a moment. Let it breathe. 9.5 trillion kilometers. If you were to write that number out in full, on a piece of paper, it would take a moment just to count the zeros. And that is only 1 light year. From here, the numbers grow. Step 4. The Milky Way. Our galaxy, the Milky Way, is a barred spiral galaxy, a flat, spinning disk of stars, gas, dust and dark matter, with long arms curling outward from a dense central core. It is approximately 100,000 light-years across. Our Sun, our ordinary, middle-aged, nothing special star, sits about 27,000 light-years from the center, somewhere in a minor spiral arm called the Orion Spur. To cross the Milky Way from one edge to the other, traveling at the speed of light, the fastest speed that anything in the universe can travel, would take 100,000 years. Not 100,000 kilometers. Not 100,000 miles. 100,000 years. 100,000 years of traveling at the maximum possible speed, and you would have crossed only our galaxy, only our small corner of the observable universe, only one island among what we now estimate to be 2 trillion others. If you could somehow look down at the Milky Way from above, which we cannot, because we are inside it, you would see a disk of light, slightly brighter at the center, with long arms of stars spiraling outward, wrapped in a haze of gas and dust. The arms would glow blue at their edges, where young stars are being born, and gold and red at their depths, where older stars live out their long, quiet lives. The whole structure would be turning, slowly, completing one revolution every 230 million years. The Milky Way contains between 200 and 400 billion stars. Most of those stars likely have planets. Many of those planets likely have moons. The sheer volume of worlds contained in this single structure is already too large for the human mind to hold. And yet, against what comes next, the Milky Way is nothing. It is a single grain of sand on an endless beach. Step 5. The observable universe. The observable universe is the bubble of space from which light has had enough time to reach us since the Big Bang, 13.8 billion years ago. Because the universe has been expanding during that entire time, the observable universe is now approximately 93 billion light-years across. Within it, there are an estimated 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars. The total number of stars in the observable universe is estimated at somewhere around 10 to the power of 24. That is a 1 followed by 24 zeros. More stars than there are grains of sand on every beach on Earth, combined, multiplied by a factor that defies language. Think about that for a moment. Every beach on Earth, every grain of sand on every shore, on every coastline, on every island and continent. Billions and billions of grains of sand, each one tiny beyond individual attention. And then multiply that number by something so large it has no name in everyday speech. That is how many stars the observable universe contains. And each of those stars is a sun. Each one is a burning sphere of plasma, held together by its own gravity, powered by nuclear fusion at its core, radiating light and heat into the space around it. Many of them are larger than our sun. Many are smaller. But all of them are suns. All of them are, in principle, the kind of thing our planet orbits. The kind of thing that makes life possible. Hold that. 93 billion light-years. 2 trillion galaxies. A number of stars that cannot be written meaningfully in any form we use in daily life. That is the observable universe. That is everything we have ever seen, or measured, or imagined, or mapped. That is the full extent of human knowledge about the scale of existence. And now we get to the thing we came here for tonight. Step 6. The Hercules-Corona Borealis Great Wall. In the year 2013, a team of astronomers announced the discovery of a structure so large that, when the measurement was first published, other scientists refused to believe it. Not because the data was wrong, not because the methodology was flawed, but because if the measurement was correct, if the structure was as large as it appeared to be, then something fundamental about our understanding of the universe was broken. The Hercules-Corona Borealis Great Wall is approximately 10 billion light-years long. 10 billion light-years. Let us place that against the scale we just built together. The Milky Way, our home, our galaxy of 400 billion stars, is 100,000 light-years across. This structure, this single, connected structure, is 100,000 times longer than our entire galaxy. If the Milky Way were a single step, the Hercules-Corona Borealis Great Wall would be a walk from one side of the Earth to the other, 10,000 steps, each one an entire galaxy wide. But even that comparison does not quite work, because we are not comparing one galaxy to this structure. We are comparing it to the observable universe itself. The observable universe, everything we have ever seen or could ever see, is 93 billion light-years across. The Hercules-Corona Borealis Great Wall is 10 billion light-years long. That means this single structure, this one thing, spans approximately 10% of the entire observable universe. 10%. Imagine looking at a map of the entire Earth, every continent, every ocean, every island, and finding a single object that covers 10% of the globe. Not a continent, not an ocean. One object. At the scale of the observable universe, that is what the Hercules-Corona Borealis Great Wall is. One structure, stretching across a tenth of everything we can see. And here is the thing that should keep you quietly, gently, irrevocably awake. This structure should not exist. Not because it is unlikely, not because it is unusual, but because, according to our best and most carefully constructed theories about how the universe works, there was not enough time after the Big Bang for anything this large to have formed. The universe is 13.8 billion years old. This structure would have required, by conservative estimates, at least 70 billion years to assemble. Some calculations push that number closer to 100 billion. The universe is less than 14 billion years old, and this structure needed 70 to 100 billion years to grow to its current size. That is not a rounding error. That is not a minor inconsistency to be smoothed over at the next conference. That is a paradox, sitting in the sky above us, 10 billion light years long, quietly existing in a universe that is not old enough to have made it. So tonight, we are going to sit with that paradox. We are going to walk toward it slowly, the way you approach something in the dark that you are not entirely sure is safe. We're going to look at how it was discovered, what it is made of, why it breaks the rules, and what its existence might mean for everything we think we know about the beginning of time. But first, just breathe. Let the scale of it settle over you like something heavy and soft and impossible. Let yourself feel the vertigo of that number. 10 billion light years. A structure so large that it should not exist in a universe that is not old enough to have made it. We are here tonight to look at it together. And we will look at it slowly, carefully, without rushing toward the conclusion, because the conclusion, when we get there, is the kind of thing you want to arrive at gently. So close your eyes for a moment if you like. Picture the ceiling above you. Picture your room. Picture your building, your street, your city. Picture the curve of the Earth from space. Picture the sun, a bright point surrounded by the sweep of planets. Picture the Milky Way, a spiral of light, enormous beyond everyday comprehension. Picture the observable universe, a bubble of light 93 billion light years wide. And then, somewhere in that bubble, imagine a structure 10 billion light years long. A wall of galaxies. A cosmic monument that the universe built before it had any right to. That is where we are going. And we are only just beginning. There is a question that follows naturally from everything we just considered, and it is a question worth sitting with before we move forward. If this structure is 10 billion light years long, if it stretches across a tenth of the observable universe, then why did we not find it sooner? Why did it take until 2013 for astronomers to notice something so impossibly, colossally large? The answer is both humbling and strange, and it tells us something important not just about this structure, but about the nature of the universe itself and about the limits of our own vision. Let us begin with a simple observation. When you step outside at night and look up at a clear sky, you see stars. Perhaps a few thousand of them, if you are far from city lights. Perhaps only a handful, if you are surrounded by the glow of a modern city. But in either case, what you see is a sky that appears to be randomly scattered with points of light. Some brighter, some dimmer, some clustered, some isolated. The whole thing giving the impression, if you look at it long enough, of a kind of beautiful, unstructured chaos. But that impression is wrong. The stars you see are not randomly distributed. They are, every single one of them, members of our galaxy. They are local. They are neighbors, in the cosmic sense of that word. The farthest star visible to the naked eye is perhaps a few thousand light years away. Against the scale of the observable universe, that is nothing. That is the thickness of a single page in a book the height of a skyscraper. Everything you can see with your eyes, every star, every planet, every smear of light that might be the Milky Way itself on a very dark night, is contained within a vanishingly small bubble around our solar system. The universe beyond that bubble is invisible to us without instruments. And even with instruments, it is not easy to see. The truth is, we could not see the Great Wall. Not because our telescopes were too small, or our computers too slow, or our mathematics too crude, but because the Hercules-Corona Borealis Great Wall is not made of visible light. It is not a glowing thing. It does not shine. It does not broadcast its presence in the wavelengths that human eyes, or most human instruments, are built to receive. To understand why, we need to understand what this structure actually is. And to understand that, we need to talk about what the universe looks like at the very largest scales, not the scale of planets, not the scale of stars, not even the scale of galaxies, but the scale at which individual galaxies are themselves too small to plot individually, and we must instead treat them as points of light scattered across a map so vast that 10 billion light years fits comfortably within its borders. At that scale, the scale of superclusters and filaments and cosmic voids, the universe does not look like anything you would recognize from a photograph of the night sky. It looks like foam. It looks like a sponge. It looks, in the most haunting and accurate description astronomers have settled on, like a web. The cosmic web. The cosmic web is the large-scale structure of the universe. It is the skeleton on which everything else is hung. It is made of filaments, long, thin threads of matter, mostly dark matter, along which galaxies tend to cluster. Between those filaments are vast, nearly empty regions called voids, bubbles of almost nothing, tens of millions of light years across, where galaxies are rare and dark matter is thin. Where the filaments intersect, matter piles up into dense knots called nodes, and those nodes are where the most massive structures in the universe live: galaxy clusters, galaxy superclusters, and things like the Hercules-Corona Borealis Great Wall. The cosmic web is not something astronomers invented to explain the data. It is something the data revealed. When you map the positions of enough galaxies across enough of the sky, the web simply appears. It emerges from the numbers like a face emerging from static, suddenly obvious, suddenly undeniable, something that was always there, waiting to be seen. There is something beautiful about that emergence. The web was always there. Long before humans existed, long before the earth existed, long before the sun existed, the cosmic web was assembling itself in the dark, its filaments growing slowly under the influence of gravity, its voids expanding slowly as matter flowed away from them into the denser regions, its nodes accumulating mass, century by century, millennium by millennium, in a process so slow that the entire history of human civilization would not register as a perceptible step. And then, tens of thousands of years after the first humans looked up at the night sky, we built instruments sensitive enough to detect the pattern. We launched telescopes into space. We developed detectors sensitive to wavelengths far beyond what our eyes can see. We wrote software to analyze the data and extract the patterns from the noise. And the web appeared. But even with all of that, even with modern telescopes and modern computers and modern mathematics, the Hercules-Corona Borealis Great Wall was hard to find. Because at a distance of 10 billion light years, ordinary galaxies are too faint to map individually in the numbers needed to reveal the structure. So the astronomers who found the Great Wall did not use galaxies. They used something else. Something far more dramatic, far more energetic, and far more useful precisely because of how rare and bright it is. They used gamma-ray bursts. A gamma-ray burst is the most energetic explosion in the observable universe. When a massive star collapses at the end of its life, or when two neutron stars spiral together and merge, the resulting event releases more energy in a matter of seconds than our sun will release in its entire 10 billion year lifetime. The flash of gamma radiation produced by these events is so intense that it can be detected from literally the other side of the observable universe. From 10, 11, 12 billion light years away, these explosions announce themselves clearly, unmistakably, like flares fired into the darkness of deep space. Think about what that means. A star dies, collapses, explodes, in a galaxy 10 billion light years away. The energy released in that explosion is almost unimaginable, and a fraction of that energy travels for 10 billion years across the expanding void of the universe, losing energy the whole way, being stretched and dimmed by the expansion of space, and still arrives at our detectors bright enough to be measured, located, and cataloged. The universe is old enough, and our instruments are sensitive enough that we can hear the screams of stars dying 10 billion years ago on the other side of the observable universe. That is what gamma-ray burst detection means in practice. It is archaeology at the scale of the cosmos. It is listening to echoes from the very deep past. Gamma-ray bursts are, in a sense, the brightest possible markers. They are the universe's way of saying, there is matter here. There is a massive star here. There is a galaxy here. Because massive stars, the kind that end their lives in gamma-ray bursts, only form in galaxies. They require the dense clouds of gas and dust that galaxies provide. They are children of galactic environments. And so when you detect a gamma-ray burst, you know, with certainty, that there is a galaxy at that location. The team that discovered the Hercules-Corona Borealis Great Wall, led by astrophysicist Istvan Horvath and his colleagues, was working with data from NASA's Swift telescope, a satellite specifically designed to detect and localize gamma-ray bursts anywhere in the sky. Swift had been operating for years, cataloging these explosions, noting their positions, recording their distances. And Horvath's team began to notice something in the data that should not have been there. When they plotted the positions of gamma-ray bursts at a particular range of distances, specifically bursts occurring between 5 and 11 billion light years away, they found a clustering. Not a random scattering of events across the sky, which is what you would expect if the underlying distribution of galaxies were smooth and even. Instead, they found a region of the sky where gamma-ray bursts were occurring far more frequently than chance would predict. A region where the density of these explosions was statistically, measurably, undeniably higher than the surrounding areas. Picture a map of the sky, points scattered across it, each point representing a gamma-ray burst detected by Swift. If the galaxies behind those points were randomly distributed, the points would be randomly distributed too. No pattern, no clustering, just noise. But that is not what the map showed. The map showed a region, a broad, extended region, where the points were denser than they should be, where the gamma-ray bursts were piling up, event after event, in a way that could not be explained by chance. The pattern was faint, subtle enough that it had taken years of data collection and careful analysis to emerge. But it was there, unmistakably, undeniably, statistically rigorously there. That excess of gamma-ray bursts told them something profound. Where there are more explosions, there are more massive stars. Where there are more massive stars, there are more galaxies. Where there are more galaxies, there is more matter. And the region of excess they found was not small. It stretched, when they mapped it carefully, across a portion of the sky corresponding to roughly 10 billion light-years in length. The first time that number appeared in their calculations, they must have checked it again. And then again. Because 10 billion light-years is not a number that should attach itself to a single structure. It is a number that belongs to the universe itself. It is the kind of number that makes you question the result, question the method, question everything, before you finally accept that the data is clean and the math is right, and the thing you have found is simply, impossibly, enormously real. And it was real. The structure was real. The clustering was statistically significant, far beyond the threshold that scientists require before they declare a discovery genuine. The probability that the pattern they observed could be the result of random chance was calculated to be less than 1 in 50,000. The Hercules-Corona Borealis Great Wall was not an artifact of measurement error or a quirk of the telescope or a trick of the data. It was a thing, a real, physical, colossal thing. But here is what makes the discovery even more remarkable and even more unsettling. The astronomers did not discover this structure by looking at it. They discovered it by listening to it. They heard the explosions of dying stars within it, brief, brilliant flashes of gamma radiation, each one marking the death of a sun far larger than our own. And from the pattern of those deaths, they reconstructed the outline of a structure they could not directly see. This is a strange and beautiful thing about the way science works at these scales. You cannot photograph the Hercules-Corona Borealis Great Wall. No telescope in the world, no matter how powerful, can produce an image of it the way you might photograph a mountain or a cloud. It is too far away, and too diffuse, and too vast. You can only infer its presence from the signals it sends, from the deaths of its stars, from the light that has been traveling toward us for billions of years, from the subtle patterns in data that most people would look at and see only noise. The astronomers who found it were not looking for something this large. They were, in a sense, not looking for it at all. They were cataloging explosions, mapping the sky, doing the careful, patient, unglamorous work that makes science possible. And then the structure announced itself, not through any single dramatic observation, but through a pattern, a statistical excess, a whisper in the data that turned out to be the largest thing anyone had ever found. There is something worth pausing over in that fact. The largest known structure in the observable universe did not announce itself with drama. It did not blaze across the sky in a way that demanded attention. It revealed itself slowly, quietly, through the accumulation of data and the careful application of mathematics, through the patient work of scientists who were paying attention to things that most of the world would consider impossibly obscure. That patience is worth honoring. The Great Wall had been there for billions of years. The gamma ray bursts within it had been detonating for just as long, stars dying, releasing their energy, sending their light across the cosmos. Some of that light has been traveling toward Earth for more than 10 billion years, crossing the void between galaxies, navigating the expansion of space, arriving at our planet and our instruments in the years since SWIFT was launched. And it was only in 2013 that anyone looked at the pattern of those arrivals and recognized what it meant. That is not a failure of science. That is science working exactly as it should. Building instruments slowly, accumulating data carefully, looking for patterns patiently, and then, when the pattern emerges, following it wherever it leads, even when it leads somewhere that breaks the rules. The Hercules-Corona Borealis Great Wall was hidden not because it was trying to hide. It was hidden because the universe is large and light is slow, and the human capacity for observation, while remarkable, is still limited by the physics of distance and time. We found it not by seeing it, but by reconstructing it from the signals of its dying stars. Think about what that means for a moment. We live on a planet orbiting a star in a galaxy that is itself smaller than a grain of sand in comparison to this structure. We built a telescope, launched it into space, and used it to detect explosions so distant that the light from them left before the Earth existed. We then analyzed the pattern of those explosions, applied mathematical tools developed over decades of cosmological research, and from the resulting numbers, we reconstructed the outline of something 10 billion light-years long. We found the largest known structure in the universe not by seeing it, but by thinking carefully about the shadows it casts in the data. There is something deeply human about that. Something that speaks to the particular kind of creativity that science requires. The ability to look at a pattern in numbers and ask, what is the real underlying thing that could produce this? What shape, what structure, what physical reality could arrange these events in this way? And the answer, arrived at through years of careful observation and rigorous mathematics, was the Hercules-Corona Borealis Great Wall, a structure 10 billion light-years long, hiding in plain sight in the data, waiting for someone to ask the right question. It waited billions of years. We found it in 2013. And what we found, it turns out, should not be possible. That is where we are going next. Before we can understand why the Hercules-Corona Borealis Great Wall is impossible, we need to understand what it is. Not in the abstract, not as a number or a statistic, but as a physical thing, a real arrangement of matter and space. Because impossibility is only meaningful against a backdrop of how things are supposed to work. And to understand how the universe is supposed to work at these scales, we need to spend some time inside the cosmic web. Imagine, for a moment, that you could leave your body behind. Not in any mystical sense. Simply, imagine that your point of view could expand, could lift free of the surface of the Earth and rise, slowly, through the atmosphere, through the orbits of the planets, out beyond the solar system, out beyond the Milky Way, out beyond the local group of galaxies, out beyond the clusters and superclusters that form our cosmic neighborhood, until you were looking at the observable universe from outside. From a vantage point so far removed that each individual galaxy is too small to see, and what you perceive instead is the large-scale pattern of all matter, everywhere, arranged across 93 billion light-years of space. What would you see? Not a uniform fog, not a smooth, even distribution of matter spread gently and consistently across the void. What you would see, what every simulation, every survey, every deep field map has confirmed, is something that looks like the inside of a loaf of bread that was baked by physics itself. You would see bubbles, great, hollow spheres of near emptiness, the voids, surrounded by thin walls and threads of matter that connected nodes of higher density. You would see a structure that is simultaneously delicate and vast, a lacework of matter and emptiness that stretches across the entire observable universe. This is the cosmic web. Take a moment to let that image settle. A web, not a random scattering of matter, not a uniform fog, not a collection of isolated objects floating in space. A web, something with structure, with pattern, with a logic to its arrangement. Something that looks, when you see the simulations and the maps, eerily like the neural networks of a brain, or the mycelium of a vast fungus, or the capillaries of a body so enormous that its cells are entire galaxies. The resemblance to biological structures is striking enough that scientists and philosophers have commented on it for decades. Not because they believe the universe is alive. It is not, at least not in any biological sense, but because the physics of gravity and expansion, operating over billions of years, produces patterns that look uncannily like the patterns produced by biological processes operating over much shorter timescales. There is something deep in the mathematics of networks that produces similar forms regardless of the scale or the medium. The voids are the bubbles, enormous spheres of space, typically ranging from 30 to 300 million light-years across, within which the density of matter is far below the cosmic average. They are not perfectly empty. There are faint galaxies within them, stray threads of gas, the occasional lonely star cluster. But compared to the regions around them, they are deserts. They are the spaces between things, the silences between words, the emptiness that gives the structure its shape. In a void, you could travel for hundreds of millions of light years and never encounter a galaxy. The nearest star system to our own, Proxima Centauri, is a little over 4 light years away, close enough that we can envision, however fancifully, a future in which we visit it. In a void, the nearest galaxy might be tens of millions of light years away. The sky, if you could stand on a planet in the deep interior of a void, would be almost completely dark. Only the faintest smudges of light, distant galaxies at the void's edges, would relieve the blackness. It would be the loneliest place in the universe. The filaments are the threads. Long, thin structures of matter, mostly dark matter but also gas, and the galaxies that cluster along them, stretching for hundreds of millions of light years, connecting one node to another. If you could see the cosmic web at full scale, the filaments would look like the threads of a spider's web, or the branches of some impossibly vast tree, or the neural pathways of a brain so large that light would take billions of years to cross it. And the nodes, the places where filaments meet, are where the most massive structures in the universe concentrate. Galaxy clusters, the largest gravitationally bound objects that exist, sit at these intersections. And where multiple clusters align along a particularly dense stretch of filament, you get something larger still, a supercluster, a structure that is not bound by gravity in the same way a cluster is, but is instead loosely connected by the geometry of the web itself. The Hercules-Corona Borealis Great Wall is not a filament. It is not a cluster. It is not a supercluster, in the way astronomers normally use that word. It is something that sits above all of those categories, a concentration of matter so extended, so continuous, so impossibly large, that it forces us to reach for new words, or to use old words in ways they were never quite meant to be used. To understand what the Great Wall is, think of the cosmic web the way you might think of a mountain range. Individual mountains are the clusters, massive, impressive, clearly defined. The ridgelines that connect them are the filaments, long, continuous structures that link one peak to the next. And occasionally, in a mountain range, you find a region where the ridgelines are particularly dense, where the peaks are particularly numerous and close together, where the terrain rises and stays high for an unusually long distance. That region, that elevated plateau of concentrated stone, is the equivalent of what the Hercules-Corona Borealis Great Wall is in the cosmic web. It is a region where the web is dense, where the filaments are thick and close together, where the clusters are numerous and the voids between them are smaller than average, where matter, in all its forms, visible and dark, has accumulated over billions of years into a structure so extensive that it dwarfs everything else we have ever mapped. Within the Hercules-Corona Borealis Great Wall, there are billions of galaxies. That is not a poetic exaggeration. That is a conservative estimate based on the density of the region and the volume it occupies. Billions of galaxies, each one a collection of hundreds of billions of stars. Each star potentially orbited by planets, each planet potentially harboring conditions that could, in principle, support chemistry and complexity, and eventually life. Think about what a galaxy is. Not as a word, not as a distant smear in a telescope image, but as a thing. A galaxy is a city of stars, a collection of hundreds of billions of suns, each one burning, radiating, warming the space around it. Some of those stars have planets. Some of those planets have water. Some of those worlds have atmospheres. A galaxy is a place where all the conditions for the unfolding of complexity are present in abundance. And within the Great Wall, there are billions of them. Billions of cities of stars. All of them embedded in a structure so large that the entire observable universe is only 9 times wider. The structure contains, within itself, a number of worlds that we cannot meaningfully count. The arithmetic leads to numbers so large that they dissolve into abstraction. Billions of galaxies, times hundreds of billions of stars per galaxy, times some fraction of stars with planets, gives you a number of potential worlds within this single structure that is larger than any quantity we have words for. And all of this, all of these galaxies, all of these stars, all of these potential worlds, is arranged in a pattern that, when viewed at the right scale, forms a single coherent thing. A wall. A great wall. Not a wall in the sense of a smooth, flat surface, but a wall in the sense of a concentrated region, a ridge, a place where the cosmic web rises up and stays up for 10 billion light years before it subsides back into the average density of the universe. The structure gets its name, Hercules-Corona Borealis, from the constellations in which we observe it. These are not constellations that have any physical relationship to the structure itself. Hercules and Corona Borealis are patterns of stars within our own Milky Way, pressed against our sky by proximity, just a few hundred light years away at most. They are our neighbors. The Great Wall is 10 billion light years behind them, so distant that the light we detect from it left before the Earth existed, so remote that to call it a neighbor of the constellations that share its name is like calling the moon a neighbor of the stars that rise above it. The name is simply a direction. When you look at the region of sky containing Hercules and Corona Borealis, and you look not at the nearby stars but through them, past them, billions of light years beyond them, you are looking toward the Hercules-Corona Borealis Great Wall. On a clear night, when those constellations are visible above you, you are looking in the direction of the largest known structure in the observable universe. You are looking across 10 billion light years of space towards something that should not exist. And the light that reaches your eyes from that direction, the faint, almost imperceptible glow of galaxies and stars at the edge of detectability, left its sources before the Earth was born. It is always there, above us, in that direction, whether we are looking or not. During the day, when the sun bleaches the sky and the stars disappear, it is still there. On cloudy nights, when every star is hidden behind gray water vapor, it is still there. When you are inside, with walls and roof between you and the sky, it is still there. 10 billion light years away, in the direction of those two constellations, a structure 10 billion light years long is hanging in space, dense with galaxies, ancient beyond comprehension, and by every account that our physics can offer, impossible. The question of what holds it together is one that reveals something important about how matter behaves at these scales. Because a structure this size, this extended, raises an obvious question: why does it not simply disperse? Why does matter at these distances remain clustered rather than spreading out evenly as the universe expands? The answer, to the extent we have one, is dark matter. Dark matter is the majority of the matter in the universe. It does not emit light. It does not absorb light. It does not interact with ordinary matter in any way we have yet been able to directly detect, except through its gravitational influence. But gravity is enough. Dark matter exerts gravity, and its gravity shapes everything. The cosmic web itself is, in a fundamental sense, a map of dark matter. The visible galaxies trace the regions where dark matter is dense, clustering along the filaments and nodes of the web the way water clusters in the low points of a landscape. Imagine a vast landscape of gentle hills and valleys. Invisible hills and invisible valleys that you cannot see or touch, but that exert a gravitational pull on everything near them. Water, if it flowed in this landscape, would collect in the valleys, tracing the low points of the terrain. Galaxies, in the landscape of dark matter, do the same thing. They collect in the regions where the dark matter is densest. They trace the filaments and nodes of a web that is mostly invisible, mostly beyond our direct perception, but whose shape we can read in the distribution of the light they emit. In the earliest moments of the universe, tiny fluctuations in density, regions that were ever so slightly more dense than their surroundings, began to grow. Dark matter, responding to gravity, fell into those fluctuations and made them denser still. Ordinary matter followed, drawn in by the gravity of the dark matter. Galaxies formed at the densest nodes. Filaments stretched between those nodes. And over billions of years, the cosmic web assembled itself, driven by the relentless pull of gravity on a universe seeded with quantum imperfections. The Hercules-Corona Borealis Great Wall is, in this framework, a region where that process happened with unusual intensity, where the initial density fluctuations were stronger or more aligned, or distributed in a pattern that allowed gravity to build something more extended and more massive than it built anywhere else. But here's the problem. Here is the thing that makes this structure not just large, but anomalous. Not just impressive, but impossible. The cosmic web takes time to build. Gravity is not fast. The process of small fluctuations growing into filaments and filaments connecting into structures is one that operates on timescales of billions of years. The largest structures in the universe today, clusters, superclusters, formed over the full 13.8 billion years of cosmic history. And they are large, hundreds of millions of light years across, but they are not this large. The Hercules-Corona Borealis Great Wall is not hundreds of millions of light years long. It is 10 billion light years long. It is 100 times longer than the largest superclusters. And for gravity to have assembled something 100 times larger, for the cosmic web to have grown filaments and ridges extended enough to produce a coherent structure on this scale, would have required not 13.8 billion years, but something more like 70 to 100 billion years. The universe is less than 14 billion years old. This structure appears to require 5 to 7 times more time than the universe has existed to form. That is the heart of the problem. That is the impossibility at the center of everything we are exploring tonight. The cosmic web is real. The structure is real. The physics of gravity and dark matter and the expansion of the universe are all real and well understood and have been tested and confirmed by observations across decades of cosmological research. And when you apply those well-understood physics to the question of how long it would have taken for the Hercules-Corona Borealis Great Wall to form, the answer comes back broken. The answer comes back with a number that is larger than the age of the universe itself. Let that settle over you for a moment, not as a source of alarm, but as a source of wonder. The largest thing we have ever found, a structure of billions of galaxies, 10 billion light years long, could not have been built by the universe we live in, not in the time available, not by the processes we understand. Something else must be at work. Something we have not yet fully understood. Something that the Great Wall is quietly, patiently, enormously pointing toward. And that something, that unknown thing at the heart of the paradox, is where we are headed next. There is a principle at the foundation of modern cosmology. It is called the cosmological principle, and it is, in a sense, the bedrock on which our entire understanding of the universe rests. Without it, cosmology as a discipline becomes nearly impossible. With it, the universe becomes tractable, measurable, a thing that obeys consistent rules and can be described by consistent mathematics. The cosmological principle states, in its simplest form, that the universe, when viewed at sufficiently large scales, is homogeneous and isotropic. Homogeneous means that it looks the same in every location. Isotropic means that it looks the same in every direction. Together, these two properties amount to a single profound claim. On the largest scales, the universe has no special places and no special directions. It is, on average, smooth. Let us sit with that claim for a moment before we examine what it means when the data challenges it. Homogeneous, isotropic, smooth. These are words that describe a universe without hierarchy, without peaks of privilege, without one place being fundamentally different from another. In a homogeneous universe, you could be dropped anywhere, in any galaxy, in any cluster, in any filament, and on average, after averaging over a large enough volume, everything would look the same. The density of matter, the temperature of space, the rate of expansion, all of it would be consistent, regardless of where you were. There is something democratic about this. Something that appeals to a deep human sense that the universe, at its most fundamental level, does not have favorites. The Earth is not the center. The Milky Way is not special. The local group is not privileged. On the largest scales, every place is as good as every other. This is not an assumption pulled from thin air. It is a principle that emerged from observation, from the fact that the cosmic microwave background, the afterglow of the Big Bang, is uniform to better than 1 part in 100,000 across the entire sky. From the fact that galaxy surveys, when averaged over large enough volumes, show a consistent density of matter in every direction we look. From the fact that the laws of physics appear to operate identically everywhere we have been able to test them. The cosmological principle is, in short, a description of a deep and tested feature of reality. And it has been extraordinarily productive. It is the reason we can model the entire universe with a single set of equations. It is the reason cosmologists can talk about the average density of matter, the average rate of expansion, the average temperature of space, without having to specify a location. Because on the largest scales, every location is, on average, the same. But there is a crucial qualifier in that principle, and it is the word I have been using carefully throughout this explanation. Sufficiently large scales. The cosmological principle does not say the universe is smooth at every scale. Obviously, it is not. Stars exist, which means matter is concentrated into dense balls of plasma surrounded by enormous volumes of empty space. Galaxies exist, which means stars themselves are concentrated into structures far denser than the average. Clusters and superclusters exist, which means galaxies cluster, and that clustering produces regions of higher density surrounded by voids. All of this is consistent with the cosmological principle, because all of this structure exists at scales small enough that when you average over a sufficiently large volume, the density comes out smooth. The principle does not forbid structure. It only says that structure, no matter how impressive at smaller scales, must average out as you zoom out to larger ones. Think of it this way. A city has enormous structure at the scale of streets and buildings. It has neighborhoods, commercial districts, parks, industrial zones. It is highly heterogeneous when you look at it up close. But zoom out far enough, to the scale of a continent, and the city becomes invisible, a tiny speck lost in the larger average of forests and fields and oceans. At the continental scale, the city's structure has averaged out into the smooth background of the landscape. The cosmological principle says that the universe does the same thing. At small scales, at the scale of stars, galaxies, clusters, it is structured, heterogeneous, full of interesting things. But at large enough scales, all of that structure averages out, and the universe becomes smooth. It becomes homogeneous. It stops having special places. There is a threshold, a scale above which, according to the cosmological principle, you should no longer find coherent structures. You should find only the smooth average of matter distributed across space. Above that threshold, the universe should look like a fog, uniform, featureless, the same in every direction and every location. That threshold is estimated to be somewhere around 300 to 400 million light years. Once you are averaging over volumes larger than that, the density of the universe should be consistent. The structure should disappear into the average. The cosmic web should resolve into smoothness. 300 million light years. That is the scale at which structure is supposed to end. The Hercules-Corona Borealis Great Wall is 10 billion light years long. Let us be precise about what that means. The Great Wall is approximately 33 times larger than the scale at which the cosmological principle says coherent structures should exist. It is not slightly larger. It is not modestly in excess of the theoretical limit. It is more than an order of magnitude beyond the point at which physics says the universe should be structureless. If the cosmological principle is correct, if the universe is truly homogeneous and isotropic at sufficiently large scales, then the Hercules-Corona Borealis Great Wall should not exist as a coherent structure. It should be an artifact, a statistical fluke, a region that looks dense but is not actually connected, not actually part of a single physical thing. It should dissolve, upon closer inspection, into the smooth background of the universe at large. But it does not dissolve. The statistical analysis has been done and redone and done again with different methods and different datasets. The clustering is real. The structure is coherent. The gamma-ray bursts that trace it are not randomly distributed. They are concentrated in a region whose size and shape correspond to something that is, by every measure available to us, a single large structure. So we have two options. Either the cosmological principle is wrong, or this structure is something our theories cannot yet explain. Neither option is comfortable. The cosmological principle being wrong would not simply mean that cosmologists made an error. It would mean that the foundational assumption on which modern cosmology is built, the assumption that underlies the Big Bang model, the dark energy model, the dark matter model, the entire framework that we use to describe the universe, is incorrect. It would mean that we have been building a cathedral on a foundation that is not level, and that the cathedral, however beautiful, however carefully constructed, is not quite right. That does not mean we would need to throw everything away. Scientific revisions are rarely total demolitions. More likely, it would mean that the cosmological principle is approximately correct, valid over a certain range of scales, but breaks down at scales larger than we have previously appreciated. It might mean that the universe is smooth on average, but that the averaging has to be done over larger volumes than we thought. Volumes so large that we have not yet surveyed enough of the universe to see the smoothness emerge. That possibility is worth pausing over. We exist inside the observable universe, inside our bubble of light, and we have mapped only a portion of it with the precision needed to test the cosmological principle rigorously. Perhaps the principle holds, but only becomes apparent at scales we have not yet fully explored. Perhaps the Great Wall is a local anomaly, an unusually large structure that would average out if we could see 10 times farther or 100 times farther than we currently can. But even that possibility, that the principle holds at scales we cannot yet probe, has consequences. Because the models we use to describe the universe, the mathematical frameworks that predict the expansion rate, the formation of structure, the distribution of dark matter, all of these are built on the assumption that the universe is smooth above a certain scale. If that scale needs to be revised, if the threshold needs to be pushed higher, then all of those models need to be adjusted too. And adjusting them might change our answers to some of the most fundamental questions in cosmology. How fast is the universe expanding? How old is it? How much dark matter does it contain? What is the nature of dark energy? All of these answers depend, to some degree, on the assumption of large-scale smoothness. If that assumption breaks, the answers might shift. The alternative, that the structure is real and the cosmological principle is intact, but our models of structure formation are wrong, is equally troubling. It would mean that the process by which the cosmic web forms, the physics of dark matter and gravity that we use to explain how structure grows over time, is missing something. Something that could produce structures 30 times larger than our models allow. Something that operates at scales we have not yet encountered in any other context. That missing something might be a new kind of physics. A process that operates at very large scales, over very long timescales, in ways that our current equations do not capture. A mechanism that can build structures faster or larger, or through a fundamentally different process than the one we currently understand. Or, and this is where the story begins to feel genuinely strange, it might not be missing physics at all. It might be physics that we know about, but that operated under conditions that no longer exist, conditions that existed before the Big Bang, or during an early phase of the universe so extreme that the rules were different from the ones that govern the universe today. We will get to that possibility. It is the deepest and most unsettling one, and it deserves its own careful examination. But before we go there, let us stay for a moment with the broken principle itself. Because there is something important in the act of sitting with a broken rule. When a principle that has worked so well for so long, a principle that underlies so much of our understanding of reality, turns out to be violated, the natural human response is discomfort. Something that was solid becomes uncertain. But that discomfort is not a sign that science has failed. It is a sign that science is working. The entire point of having principles is to test them. The entire point of building models is to push them to their limits and see where they break. The cosmological principle has been tested for decades with ever more precise instruments and ever larger surveys. And in that testing, it has held up remarkably well. Until now. The Hercules-Corona Borealis Great Wall is one of several structures that have been pushing at the edges of the principle's validity. There are other very large structures, the Sloan Great Wall, the Huge Large Quasar Group, the South Pole Wall, that also probe the boundary between permitted and impossible. The Great Wall is the largest and most anomalous of them, but it is not entirely alone in its strangeness. What all of these structures share is the quality of being unexpectedly large, of sitting at or beyond the scale where the cosmological principle says they should not be coherent structures at all. And the fact that there are several of them, not just one, makes it harder to dismiss any individual case as a statistical fluke. A single anomaly can be a fluke. A pattern of anomalies begins to look like a message. What the message says, that is what we are trying to understand. It might say that our models need adjustment. It might say that the cosmological principle needs refinement. It might say that the universe, at its largest scales, is doing something that we have never seen before and do not yet have the language to describe. Or it might say something even stranger, something that reaches back beyond the beginning of the universe as we know it, back to whatever came before the Big Bang, if anything came before, back to a time and a set of conditions so alien to our experience that the structures they produced look, from our vantage point inside a universe only 13.8 billion years old, like impossibilities. We are not yet at the point of claiming we know what the message says. We are at the point of recognizing that there is a message. And that recognition, that willingness to look at the data and say, something here does not fit, something here breaks the rules, something here demands an explanation that our current framework cannot provide, is both the most uncomfortable and the most exciting place that science can be. So let the discomfort sit for a moment. Let the broken principle be present without rushing to fix it. The cosmological principle says the universe should be smooth above 300 million light years. The Hercules-Corona Borealis Great Wall is 10 billion light years of coherent structure. Those two facts do not fit together. And that tension, that irresolvable, data-backed, physics-breaking tension, is not a problem to be solved tonight. It is a question to be held, gently, in the dark, with the weight of 10 billion light years pressing down on it from above. We have been circling the paradox. We have approached it from the direction of scale, from the direction of discovery, from the direction of the cosmic web, from the direction of the broken principle. Now it is time to stand directly in front of it and look at it without flinching. Because the time paradox at the heart of the Hercules-Corona Borealis Great Wall is not just a curiosity, not just an interesting footnote in the history of cosmology. It is a genuine, deep, irreducible problem, one that cuts to the core of what we think we know about how the universe began, how it evolved, and what it is capable of producing. Let me ask you something before we begin. Have you ever watched a tree grow? Not in the sense of standing in front of a sapling and watching it in real time. Trees grow too slowly for that. But have you ever looked at a photograph of a forest taken 10 years ago and then looked at the same forest today and seen how much it has changed? The trees that were saplings are now young adults. The gaps in the canopy have closed. The undergrowth has shifted. A forest grows on a timescale that is long by human standards, but comprehensible. You can see the growth because you can compare the past to the present. Now imagine you are shown a photograph of a fully grown redwood forest. Trees 300 feet tall, trunks 12 feet across, canopies so dense they block the sunlight, and you are told that the seed for this forest was planted yesterday. That is the situation with the Hercules-Corona Borealis Great Wall. We are looking at a fully grown forest, vast, dense, structured, and the mathematics tells us the seed was planted far too recently for what we see to be possible. To understand the paradox fully, we need to understand how structures form in the universe. Not in a loose, metaphorical way, but in a precise enough way that the timescales involved become real. Because the paradox lives in the timescales. The paradox is built out of the difference between how long the universe has existed and how long it would have needed to exist to build the thing we have found. When the Big Bang occurred, 13.8 billion years ago, the universe was not a void into which matter was suddenly thrown. It was a state, an enormously hot, enormously dense state in which all of the matter and energy that would eventually become everything we see was compressed into a volume incomprehensibly smaller than the universe today. In those first moments, the universe was as smooth as it has ever been. The density was nearly perfectly uniform in every direction. Nearly, not perfectly. There were fluctuations, tiny, quantum-scale variations in density, regions that were, by an infinitesimally small amount, more dense than their surroundings, and regions that were, by an equally small amount, less dense. These fluctuations were not put there by accident. They were a consequence of quantum mechanics, of the irreducible uncertainty that governs the behavior of matter at the smallest scales. And they were the seeds of everything. Think about what that means. The quantum fluctuations in the density of the newborn universe, variations smaller than anything we could measure with any instrument we have ever built, became, over billions of years, every galaxy, every cluster, every filament, every supercluster. The cosmic web, with all its complexity and beauty, grew from seeds that were, at the beginning, unimaginably small. The structure of the universe today is a record of quantum events that happened in the first instance of time. Over time, gravity amplified those seeds. The regions that were slightly more dense attracted more matter. More matter made them denser still. More density attracted more matter. This is the process of gravitational collapse, and it is the engine that built everything in the universe, from the smallest asteroid to the largest supercluster. But gravitational collapse takes time. Gravity is not fast. The rate at which a fluctuation grows, the rate at which a region of slightly above average density becomes a gravitationally significant structure, depends on the size of the region. Small fluctuations grow into planets and stars relatively quickly. Larger fluctuations grow more slowly. And the largest fluctuations, the ones that eventually become galaxy clusters and superclusters, grow the most slowly of all. Cosmologists have a mathematical framework for describing this process. It is called linear perturbation theory, and it tells us, with considerable precision, how quickly a fluctuation of a given size will grow under the influence of gravity in a universe expanding at a known rate. The framework has been tested against observations of the cosmic microwave background, against surveys of galaxy clustering, against measurements of the large-scale structure of the universe, and it works. It fits the data. It correctly predicts the sizes and abundances of the structures we observe. When you apply that framework to the Hercules-Corona Borealis Great Wall, asking how long it would have taken for a fluctuation to grow into a coherent structure 10 billion light-years across, the answer it returns is not 13.8 billion years. The answer it returns is between 70 and 100 billion years. 70 to 100 billion years, compared to the 13.8 billion years the universe has had to work with. This is not a small discrepancy that might be resolved by more precise measurements or better data. This is a factor of 5 to 7. A factor so large that it cannot be attributed to uncertainty in the parameters, or to limitations of the observational method, or to some systematic error in the analysis. The structure is simply too large to have formed in the time available. Let us sit with that sentence for a moment. Not rushing past it, not hurrying toward the explanation, just letting the paradox be present in its full weight. The structure is too large to have formed in the time available. The universe is 13.8 billion years old. This structure needed 70 to 100 billion years to form. The universe is too young, by a factor of 5 to 7. 5 to 7. not 5 to 7%, 5 to 7 times. If someone told you that they had run a marathon in under 2 hours, and then you discovered that their stopwatch recorded a time of 10 to 14 hours, you would not describe that as a small discrepancy. You would describe it as impossible. You would conclude that something was fundamentally wrong with either the claim or the stopwatch. With the Great Wall, the claim is the observation, real, measured, statistically confirmed. So it is the stopwatch that must be questioned. And the stopwatch, in this case, is the age of the universe, or the rate at which structures grow, or the nature of the initial conditions, or something else entirely, something we have not yet thought to question. To make this more concrete, consider an analogy. Imagine you are an archaeologist, and you have found a medieval cathedral, a full cathedral, with carved stonework, stained glass windows, flying buttresses, a vaulted ceiling 100 meters high. But when you date the materials, you find that the oldest stone in the building is only 50 years old. Medieval cathedrals take centuries to build. The one in front of you, according to your best understanding of how cathedrals are constructed, could not have been built in 50 years. And yet here it is, complete, magnificent, impossible. That is the situation with the Hercules-Corona Borealis Great Wall. We have found the cathedral. We have dated the stone. And the stone is too young for the cathedral to exist. You can walk around the cathedral. You can touch its walls and look up at its ceiling and feel the coolness of its interior and hear the echo of your footsteps. It is real. Its existence is not in doubt. And yet your best understanding of how such things come to be says it could not have been built in the time available. Now, there are a few ways to respond to this situation. You might conclude that your understanding of how cathedrals are built is wrong, that somehow, in this particular case, the process was dramatically faster than you thought possible. You might conclude that the dating method is flawed, that the stone is actually much older than it appears. Or you might conclude that the cathedral was not built the way cathedrals are normally built, that some extraordinary process, some unprecedented technique, some condition unique to this particular site, produced something that ordinary cathedral building could never have achieved. In cosmological terms, these possibilities translate as follows. First possibility, our models of structure formation are wrong. The framework we use to predict how quickly the cosmic web builds its structures is incomplete, missing some process that allows gravity to act more efficiently at very large scales, assembling structures faster than our equations predict. If this is true, the paradox dissolves, but the price we pay is the admission that our best theories of cosmology need significant revision. Second possibility, our measurement of the structure is wrong. Perhaps the Hercules-Corona Borealis Great Wall is not actually as coherent as it appears. Perhaps the clustering of gamma-ray bursts that was used to infer its existence is not a reflection of a single connected structure, but rather a superposition, a chance alignment of several smaller structures that happen to lie in the same direction from our perspective. This possibility has been seriously considered and seriously tested, and the tests have consistently supported the reality of the structure. But science demands that all possibilities remain on the table until they are definitively ruled out. Third possibility, the structure formed through a process that we do not yet understand, one that operates outside the standard framework of gravitational collapse in an expanding universe, one that perhaps began before the Big Bang, or during an early phase of the universe so extreme that our ordinary cosmological equations do not apply. The third possibility is the one that unsettles most. It is also the one that is most scientifically interesting. Because if the Hercules-Corona Borealis Great Wall could not have formed through the processes we understand, then its existence is telling us something fundamental about the universe that we do not yet know. Something that is larger than the discrepancy between a predicted formation time and an observed formation time. Something that reaches into the foundations of cosmology and pulls at the threads that hold the model together. Something that may, when we finally understand it, change not just our understanding of the Great Wall, but our understanding of everything. The time paradox also has a deeper resonance if you allow yourself to feel it. We are not just talking about a structural engineering problem in cosmology, a mismatch between a predicted formation time and an observed formation time. We are talking about the possibility that the universe, as we understand it, did not have time to make one of the largest things it contains. The universe did not have time to make one of the largest things it contains. Read that sentence again, slowly. Let it breathe. The universe did not have time. The thing that has existed for 13.8 billion years, the thing that contains 2 trillion galaxies and a septillion stars, did not have time. Was not old enough. Was too young. For a structure 10 billion light years long to have formed the way we think structures form, for the seeds to have been planted and the roots to have grown, and the branches to have extended across 10 billion light years of space, the universe would need to be 5 to 7 times older than it is. And it is not. None of these possibilities is comfortable. All of them are worth taking seriously. And all of them lead, one way or another, to the same conclusion. The Hercules-Corona Borealis Great Wall is not just the largest structure in the observable universe. It is a problem. A beautiful, enormous, 10 billion light-year long problem that the universe has handed to cosmology, and that cosmology has not yet solved. Let that settle over you like the darkness that settles at the end of day. Not a frightening darkness, not a hostile one, but a quiet, expansive darkness that contains, somewhere within it, the outline of something extraordinary. The time paradox is not a dead end. It is a corridor. And at the end of that corridor, past the broken principle and the impossible timescale, there are possibilities that we have not yet fully explored. We are going to explore them now. Slowly, carefully, with the weight of 10 billion light years pressing on every word. There is a phrase that cosmologists use, quietly, among themselves, when they encounter structures at the boundary of what their models permit. They call it the end of greatness. It is not a phrase you will find in most textbooks. It is not a technical term with a precise mathematical definition. It is something closer to a philosophical marker, a point on the map of the universe where human imagination reaches its limit and begins to fail. Take a moment to feel the weight of that phrase. The end of greatness. Not the end of size, not the end of distance, not the end of number. The end of greatness. The point at which things stop being great, stop being distinct, identifiable, remarkable, and dissolve instead into the undifferentiated average of everything. The point where the universe stops having things in it and becomes simply itself. The end of greatness refers to the scale at which the universe stops looking structured. Below that scale, at the scale of galaxies, clusters, superclusters, the universe is full of distinct, recognizable things. Things with edges and centers. Things that can be pointed to and named. Things that are clearly different from what surrounds them. But above that scale, above the threshold where the cosmological principle says smoothness should prevail, there are, in principle, no more distinct things. There is only the average, only the fog, only the undifferentiated background of matter spread evenly across space. The end of greatness is the point where naming stops being useful, where the universe becomes too large for things to have identities, where you can no longer say, here is this, and there is that, because everything has dissolved into everything else. It was supposed to occur at around 300 million light years. Beyond that scale, cosmologists expected to find only smoothness, only the quiet, featureless average of a universe that, at its largest scales, looks the same everywhere. The Hercules-Corona Borealis Great Wall is 10 billion light-years long. It is a distinct, named, identifiable thing at a scale 33 times larger than where the end of greatness was supposed to be. In other words, the end of greatness has not ended. The universe is still producing identifiable structures at scales where it should only be producing fog. And that failure of the fog to appear, that persistence of structure beyond the point where structure is permitted, is one of the most quietly unsettling things about the Great Wall. To understand why it is unsettling, it helps to sit with what the end of greatness actually represents. When cosmologists say that the universe becomes smooth above a certain scale, they are not making an aesthetic observation. They are making a physical claim about how structure forms. They are saying that the process of gravitational collapse, operating over the time available since the Big Bang, can only produce structures up to a certain size. Above that size, there simply has not been enough time for the seeds of structure to grow, for matter to concentrate, for coherent things to emerge from the background. If the end of greatness occurs where the models predict, it is confirmation that those models are correct. It is evidence that the Big Bang happened when and how we think it did, that the universe has been expanding at the rate we think it has, that dark matter and gravity have been working as we think they have, for the time we think they have been working. If the end of greatness does not occur where the models predict, if structure persists beyond the predicted threshold, it means something in that chain of assumptions is wrong. Something about the timing, the rate, the mechanism, the initial conditions, or the fundamental physics needs to be revised. The Hercules-Corona Borealis Great Wall is, in this sense, not just an impressive discovery. It is a challenge to the entire framework of modern cosmology. It is the universe's way of saying, your model of me is not complete. Let us stay for a while with the scale of this challenge. Not the scale of the structure itself. We have spent considerable time there, but the scale of the intellectual challenge it poses. Because one of the things that makes the Great Wall so interesting, so worth carrying with you into the quiet of this evening, is not just that it is large. It is that it is large in a way that matters, in a way that carries consequences. Imagine you are a cartographer. You have spent your entire life making maps of a particular region, a vast, complex landscape of mountains and valleys and rivers and forests. Your maps are good. They have been tested by every explorer who has used them. The mountains are where you say they are. The rivers flow in the directions you have drawn. The forests are as dense or as sparse as your symbols indicate. You are proud of your maps, and you should be. They represent decades of careful work, and they have helped people navigate territory they could not otherwise have crossed. And then an explorer returns from a part of the landscape your maps have not yet covered, a distant region at the edge of the known territory, and tells you that there is a mountain range there so large it does not fit in the conventions of your mapping system. Not a mountain larger than the ones you have already mapped. A mountain range 33 times larger than the largest feature your system was designed to represent. Your first response might be disbelief. Your system is good. Your conventions are tested. There cannot be a feature that large. Your maps say so. But the explorer has measurements. Multiple measurements, made with different instruments, yielding consistent results. And the measurements say the mountain range is there. That is the situation with the end of greatness and the Hercules-Corona Borealis Great Wall. The cosmological maps say the end of greatness occurs at 300 million light-years. The Great Wall is 33 times larger than the largest feature those maps were designed to represent. And the measurements, the gamma-ray burst data, the statistical analysis, the independent confirmations, say the Great Wall is there. The maps need to be redrawn. Now, this does not mean the existing maps are useless. The cartographers' maps of the region they have carefully surveyed are still good. They are still accurate within their domain. They still help explorers navigate the territory they cover. Only the edge needs to be extended, the conventions revised to accommodate a feature larger than the system was designed to handle. Similarly, the cosmological models are still accurate within their domain. They still correctly predict the temperature of the cosmic microwave background, the abundance of light elements, the distribution of galaxies at intermediate scales. Only the upper boundary needs to be revised, the models extended to accommodate a structure larger than they were designed to predict. But that revision is not trivial. It is not a small correction. It is a fundamental extension of the framework, one that may require new physics, new assumptions, new ways of thinking about the initial conditions of the universe. The end of greatness was supposed to be a boundary, a point beyond which the universe had nothing new to say. But the Great Wall is the universe continuing to speak at a scale where it should have fallen silent. And what it is saying, in that low, vast, 10 billion light-year voice, is something that we are still learning how to hear. There is another layer to this that is worth bringing into the light. The end of greatness was, in a certain sense, a comfort. Not just a physical prediction, but a psychological one. It told us that the universe, however vast, was ultimately comprehensible, that there were limits to its complexity, that above a certain scale, everything smoothed out into a uniform background that required no further special explanation. The universe, in that picture, had a kind of ceiling to its strangeness. Below 300 million light-years, things were complex, varied, requiring detailed explanation. Above it, things were simple, uniform, requiring only the broad brushstrokes of the standard cosmological model. The Great Wall removes that ceiling, or at least it pushes it much higher. It says that the universe is strange at scales we had thought were safely beyond the reach of strangeness. That complexity and deviation and the need for special explanation, these things do not end at 300 million light-years. They persist, at least in some places, out to scales of 10 billion light-years and possibly beyond. That is a more demanding universe than the one the end of greatness was supposed to describe. A universe that keeps producing surprises further out, that keeps requiring explanation at scales where explanation was supposed to give way to simplicity. And it is also, in a strange way, a more interesting universe. A universe that keeps speaking at scales where it should have gone quiet is a universe that has more to say than we thought. More to reveal, more to teach. The end of greatness has not ended. It has only moved farther out, into scales we are only beginning to probe. And the Hercules-Corona Borealis Great Wall is the evidence that it moved. Think about what it means to live in that kind of universe. A universe that refuses to become simple. A universe that keeps producing structure, keeps generating complexity, keeps requiring explanation, all the way out to the very edge of what we can observe. That is not a universe that is running out of things to say. That is a universe that is still, after 13.8 billion years, in the middle of its story. And we, here, now, with our instruments and our mathematics and our slowly improving understanding, are listening to it. We are at the edge of what we can hear, and what we hear at that edge is the Hercules-Corona Borealis Great Wall. The universe speaking at a scale where speaking was not supposed to be possible. So let the end of greatness sit with you not as a closed door, but as an open question. Let the image of a universe that refuses to become smooth, that insists on producing structure beyond its own supposed limits, be something you hold gently in the darkness. The universe is larger and stranger and more structurally complex than our best models predicted. That is not a reason for alarm. It is a reason for wonder, and for the particular kind of productive discomfort that has always driven science forward, The discomfort of knowing that there is more to understand, that the map is not yet complete, that somewhere in the data, the universe is still hiding things that will break the next set of rules we build for it. The end of greatness has not ended. It has only moved. And the Hercules-Corona Borealis Great Wall is 10 billion light years of evidence that it moved. That is where we are. And there is still more to come. We have been speaking about the Hercules-Corona Borealis Great Wall in the language of physics and statistics and broken principles. We have talked about it as an anomaly, as a paradox, as a challenge to the cosmological model. And all of that is true, and all of that matters. But there is another way to think about this structure, and tonight I want to spend some time there. Not in the language of the impossible, but in the language of the interior. Because the Great Wall is not just large. It is inhabited, or at least it could be. The billions of galaxies within it are not abstract points in a statistical distribution. They are places. Real, physical, three-dimensional places, each one a collection of stars and gas and dust and dark matter. Each one potentially hosting planets. Each one potentially hosting conditions that are, in principle, not so different from the conditions in our own Milky Way. Let us go inside the wall for a moment. Not literally. The physics of distance makes that impossible in any meaningful sense, and the light from those galaxies left before the Earth existed. So what we would be visiting, if we could visit, is the past rather than the present. But imaginatively, conceptually, let us follow the logic of what must be in there, based on what we know about galaxies and stars and the processes that govern them. Picture yourself for a moment on a planet, any planet, somewhere within the Great Wall. The planet is not real, of course. We have no evidence for any specific planet within this structure, and we are unlikely ever to obtain such evidence. But the existence of planets within the Great Wall is not speculative. It is a near certainty, given what we know about how planetary systems form. So imagine yourself on one. The sky above you, on this imagined world, looks nothing like our night sky. Your planet orbits a star, and that star is one of hundreds of billions within your galaxy. The night side of your sky might be brilliant with the light of a dense star field, or quiet and dark, if your planet lies in a sparse outer arm. But in every direction you look, you are surrounded by the light of stars that are, themselves, surrounded by the light of other galaxies. Galaxies that your descendants, if they developed the technology to look, would find to be dense beyond reckoning with other worlds like yours. You would not know, from the surface of that imagined planet, that you lived inside the largest known structure in the observable universe. The structure is too big to perceive from within it. It is like trying to see the shape of a continent while standing on a beach. The local detail overwhelms the global pattern. Your sky would show you your star, your galaxy, perhaps the faint smear of a neighboring galaxy. But the 10 billion light-year wall that your galaxy is part of would be as invisible to you as it is to us. This is a strange and humbling thought. The largest thing in the observable universe is invisible from within itself. The creatures who might live inside it would have no direct experience of its scale. They would have to do exactly what we do: build telescopes, develop mathematics, map the positions of distant explosions, and slowly, painstakingly, reconstruct the shape of the structure they cannot see from inside. Within the Hercules-Corona Borealis Great Wall, there are billions of galaxies. That is not a poetic exaggeration. That is a conservative estimate based on the density of the region and the volume it occupies. Billions of galaxies, each one a collection of hundreds of billions of stars, each star potentially orbited by planets, each planet potentially harboring conditions that could, in principle, support chemistry and complexity, and eventually life. The structure contains, within itself, a number of worlds that we cannot meaningfully count. The arithmetic leads to numbers so large that they dissolve into abstraction. Billions of galaxies, times hundreds of billions of stars per galaxy, times some fraction of stars with planets, gives you a number of potential worlds within this single structure that is larger than any quantity we have common words for. And on some of those worlds, perhaps on many of them, chemistry happened. The same chemistry that happened on Earth. Carbon bonding with hydrogen and oxygen and nitrogen. Molecules of increasing complexity assembling in warm, liquid environments. The long, slow, improbable, inevitable process by which chemistry becomes biology, by which inert matter acquires the capacity to replicate itself, to evolve, to grow more complex over time. We do not know how common life is. We do not yet know whether life arose on Earth through processes that are rare or common, fragile or robust. The question of whether life exists elsewhere in the universe is one of the most important unanswered questions in all of science. But the Hercules-Corona Borealis Great Wall, by its sheer size, by the sheer number of worlds it contains, is a kind of statistical argument for the possibility of company. Even if life is extraordinarily rare, even if only 1 in a billion planets ever develops it, the number of planets within the Great Wall is so large that the expected number of living worlds would still be vast. Even 1 in a trillion would yield a number of living worlds that our imagination cannot contain. This is not a claim that life is there. It is an observation that the Great Wall provides the largest possible canvas for the question. Whatever the probability of life per planet, the Great Wall maximizes the number of trials. It is the universe's largest experiment in the conditions for complexity. And if life arose on some of those worlds, if biology happened, then evolution happened too. The same blind, unpredictable, extraordinarily powerful process that transformed single cells into the full diversity of life on Earth. Evolution operating over hundreds of millions or billions of years on world after world, producing forms that we cannot imagine and would not recognize if we saw them. Think about the diversity of life on Earth alone. From the simplest bacteria to the blue whale. From the desert cactus to the deep-sea anglerfish. From the virus to the redwood forest. All of that extraordinary variety, all of that biological complexity, produced by a single process, operating on a single planet, over less than 4 billion years. Now multiply that by the number of worlds in the Great Wall, by the number of different planetary environments, different temperatures, different gravities, different atmospheric compositions, different orbital periods, different stellar spectra. Each environment a different pressure on evolution. Each pressure producing different adaptations. Each adaptation opening new ecological niches. Each new niche supporting new forms of life. The Great Wall, if it contains life, contains more variety, more biological complexity, more forms of existence than the human mind can begin to approach. It contains the equivalent of trillions of Earths, each one running its own 4 billion-year experiment in the possibilities of chemistry and evolution and complexity. And if evolution happened, then, in at least some cases, it produced beings capable of looking up, of noticing the sky, of asking questions about the scale of things, of building instruments and developing mathematics and gradually, painstakingly, constructing a picture of the universe they inhabit. Within the Hercules-Corona Borealis Great Wall, there may be civilizations. There may be beings who have looked at their own night skies and asked the same questions we ask, who have mapped their own galaxies and discovered the cosmic web and found, at the largest scales, something that breaks their models too, who sit in their equivalents of quiet rooms and try to understand what they have found. Perhaps some of those civilizations are far older than ours. Perhaps they have been asking these questions for millions of years. Perhaps they have developed technologies and understandings that would make our current knowledge look like the first tentative scratches of a child learning to draw. Perhaps they have answers to questions we have not yet thought to ask. We will never know. The distances involved make communication or contact, or even confirmation, impossible on any timescale that matters to us. The light from those galaxies took billions of years to reach us, and any light we send toward them will arrive billions of years in the future, by which time whatever civilizations exist, there will have had billions of years to rise and fall and change beyond recognition or disappear entirely. We are separated not just by distance, but by time, by the unbridgeable gap between what was and what is and what will be. But the possibility is there. The possibility that within the structure we have been discussing tonight, within this 10 billion light-year anomaly that breaks the cosmological principle and defies the time constraints of the standard model, there exist, or have existed, or will exist, beings who are asking their own version of our questions. There is a strange comfort in that possibility. Not the comfort of certainty, we have none, but the comfort of scale. The universe is not just large, it is so large that even very unlikely things happen many times within it. And the things that happen within the Great Wall are separated from us by distances so immense that they constitute, in a meaningful sense, other realms of experience, other contexts in which questions are asked and answers are sought. Let the interior of the wall be present for a moment, not as a physics problem, not as a cosmological anomaly, but as a place, a vast, ancient, impossibly large place, filled with galaxies and stars and worlds and perhaps, with the particular kind of matter that has learned to think about itself. We are here, doing exactly that, thinking about ourselves and about the structure we have found and about what it might contain. And somewhere, within 10 billion light-years of cosmic web, something else might be doing the same. That thought deserves to be held carefully, in the dark, with the same quiet attention that the Great Wall itself deserves. Not solved, not resolved, just held. Because the Great Wall is not just a problem for cosmology. It is a home for stars, a canvas for planets, a stage for chemistry and biology and complexity, and perhaps, in some of its billions of galaxies, a setting for the particular kind of wonder that arises when matter becomes aware of itself and looks outward and asks, how large is this? How old? How far does it go? We are here, asking those questions about the Great Wall. And the Great Wall, in its silent, colossal way, is part of the answer to every question anything within it might ask about itself. That is a strange and beautiful loop, and it deserves a moment of quiet recognition before we move on. We have arrived at the point in our journey where the questions become harder, where the comfortable framing of the problem, a large structure, a broken principle, a time paradox, gives way to something more fundamental. Something that requires us to ask not just what the Great Wall tells us about structure formation, or about the cosmological principle, or about the scale of things, but what it tells us about the map itself. Every field of human knowledge has a map. Not a physical map, not a paper chart, but a conceptual map. A model of how things work. A framework for understanding why the world is the way it is. Medicine has its map of the human body. Chemistry has its map of the elements and their interactions. Physics has its map of the fundamental forces and the particles that carry them. These maps are not the territory. They are representations of the territory, simplified, abstracted, summarized in ways that make the territory navigable. A map of a city is useful even though it does not show the individual bricks in the road, or the height of every building, or the location of every tree. The omissions do not matter for the purpose of getting from one place to another. The map captures what is needed and leaves out what is not. But every map has edges. Every map has a boundary beyond which it stops being reliable. The city map does not help you navigate the countryside beyond the city limits. The chemistry textbook does not help you understand the physics of black holes. The map of classical mechanics does not help you understand the behavior of electrons in a quantum computer. Cosmology's map is called lambda CDM. The letters stand for lambda, which represents the cosmological constant, Einstein's term for the energy of empty space, what we now call dark energy, and CDM, which stands for cold dark matter, the invisible, non-interacting substance that makes up approximately 27% of the total energy content of the universe. Together, dark energy and dark matter account for roughly 95% of everything. The ordinary matter that makes up stars, planets, gas, dust, and us, everything we can see or touch or measure directly, is only about 5%. This is already a strange and humbling map. A picture of the universe in which almost everything is invisible to us, in which the scaffolding and the engine that drive everything we observe are fundamentally beyond our direct perception. We are, in a meaningful sense, living in a universe we cannot see. Only 5% of it is made of the stuff we are made of. The rest is dark, inferred, modeled, detected only through its gravitational effects, present everywhere, but invisible to every instrument we have ever built. And yet the map works. Lambda CDM correctly predicts the temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, imprinted across the entire sky. It correctly predicts the abundance of light elements formed in the first minutes after the Big Bang, the hydrogen, helium, and lithium that make up the first generation of matter. It correctly predicts the rate of expansion of the universe, the way distant galaxies are receding from us, faster the farther away they are. It correctly predicts the large-scale structure of the cosmic web, the clustering of galaxies, the distribution of voids, the pattern of filaments. It is, by any measure, a triumph of scientific reasoning. A map that was drawn from first principles and observations, and that has been confirmed again and again by independent measurements using independent methods. When a map works this well, it is natural to trust it. Natural to believe that the territory it describes is accurately represented. And then the Hercules-Corona Borealis Great Wall appears, and the map does not know what to do with it. The challenge comes not from a single number being wrong. It comes from the cumulative weight of what the Great Wall represents. Because the Great Wall is not just an anomaly in isolation. It is part of a pattern, a growing list of observations at the largest scales that sit uncomfortably with the predictions of lambda CDM. There is the Great Wall itself, too large, by the model's own predictions, to have formed in the available time. There is the Sloan Great Wall, discovered in 2003, which stretches more than 1.5 billion light years and itself challenged the predictions of the Standard Model when it was found. There is the Huge Large Quasar Group, a cluster of quasars spanning 4 billion light years, discovered in 2012, which was immediately identified as being far too large for the Standard Model to comfortably accommodate. There is the South Pole Wall, discovered in 2020, another massive concentration of galaxies that extends at least 300 million light years in our cosmic neighborhood, sitting right at the boundary of what the model permits. Each of these structures, individually, might be explained as a statistical outlier, a rare fluctuation that happens to be larger than expected but is still within the bounds of possibility. But together, they form a pattern of large-scale structures that are systematically larger than what the model predicts should be common. A pattern of anomalies at the upper end of the size distribution, structures that are always pushing at the ceiling of what the model allows, and in the case of the Great Wall, pushing through it. When anomalies cluster, when they appear repeatedly in different places using different methods identified by different research teams, they stop being flukes and start being signals. They stop saying, something unusual happened here, and start saying, something systematic is happening everywhere that we look at the largest scales. That shift from individual anomaly to systematic signal is the point at which the map becomes suspect. Think about what it would mean for the map to be wrong. Not wrong in the way that a slightly inaccurate street map is wrong, showing a road that is 3 meters wider than it actually is, or a park that is slightly smaller than indicated. But wrong in the way that a map is wrong when it places a mountain range in the wrong location. Functionally wrong. Wrong in a way that matters. If lambda CDM is wrong at the largest scales, if its predictions for the sizes of cosmic structures are systematically too small, then the model is missing something. Something that operates at very large scales and over very long timescales. Something that allows structure to grow faster or larger than the standard equations predict. That missing something could take many forms. Perhaps the initial conditions of the universe, the distribution of density fluctuations immediately after the Big Bang, were not as simple as lambda CDM assumes. Perhaps the fluctuations were not random and Gaussian, but had some structure, some non-Gaussian features, that allowed particularly large coherent regions to form and grow more rapidly than the standard model predicts. Gaussian is a word that mathematicians use to describe a particular kind of randomness, the randomness of a bell curve, where most values cluster near the average and extreme values become exponentially less likely. If the density fluctuations in the early universe were non-Gaussian, if they had fat tails, if extreme values were more likely than a bell curve would predict, then very large structures could form more readily than lambda CDM expects. This is a testable possibility. The pattern of fluctuations in the early universe is imprinted on the cosmic microwave background, and measurements of that background can, in principle, detect non-Gaussianity. Current measurements have not definitively found it, but the measurements are still improving, and future experiments may be sensitive enough to detect the subtle signatures that current instruments miss. Perhaps dark energy is not constant, as lambda CDM assumes, but varied in strength over the history of the universe. Dark energy, in its current form in the model, is a fixed property of space, a constant energy density that does not change as the universe expands. But theoretical physicists have proposed many alternatives, forms of dark energy that vary over time, that interact with dark matter, that have a more complex behavior than the simple constant that Einstein introduced. If dark energy was weaker in the early universe and stronger later, or stronger early and weaker later, the growth rate of cosmic structures would have been different from what lambda CDM predicts. And a different growth rate could, in principle, allow larger structures to form in the time available. Perhaps dark matter has properties, self-interactions, or decay channels, or couplings to other particles that are not captured in the cold dark matter paradigm. Cold dark matter, the CDM in lambda CDM, is assumed to be a simple substance. It has mass, it has gravity, it does not interact with ordinary matter or with itself except through gravity. But this simplicity is an assumption, not a confirmed fact. Dark matter might be more complex. It might have its own forces, its own interactions, its own dynamics. And those additional properties might affect the way it clusters, the way it drives the formation of large-scale structure, in ways that lambda CDM does not capture. Each of these possibilities would change the map. Each would require revision of some part of the model. And each would make predictions that could, in principle, be tested by future observations. The map is not broken beyond repair, but the Great Wall is showing us, clearly and unambiguously, that the map needs to grow, that the territory it covers is larger and stranger than the current edition indicates. And the next edition, the one that will incorporate what we learn from structures like the Great Wall, may look significantly different from the one we have now. It will need to accommodate structures 33 times larger than the current model allows. It will need to explain, from first principles, why something 10 billion light years long can exist in a universe that is less than 14 billion years old. It will need to be a bigger map, a more ambitious map, a map that is humble enough to acknowledge what it does not yet know and bold enough to venture into the territory beyond its current edges. That process of revision, of building a better map, is not a failure. It is the most fundamental activity of science. The willingness to look at the territory and say, the map is not matching what I see, and then to sit with that discrepancy carefully, patiently, until a better map emerges. The Great Wall is showing us where the current map ends. And that ending, that edge of the known, is not a place to stop. It is a place to begin. The next map is out there, waiting to be drawn. And the Great Wall is its first landmark. There is a question that we have been approaching all evening, one that I have mentioned only in passing, in the way you might circle around something in the dark without quite looking at it directly. It is time to look at it directly now, because it is the strangest possibility of all and the most unsettling, and in some ways the most beautiful, and it emerges naturally from everything we have discussed. The question is this: what if the Hercules-Corona Borealis Great Wall began to form before the Big Bang? Let me be careful here, because this sentence requires careful handling. It is easy to hear those words and dismiss them as speculation, as science fiction dressed in the language of physics. But what I am describing is not speculation in the casual sense. It is a genuine scientific possibility, one that emerges from the mathematics of inflation, from the physics of quantum fields, from serious theoretical work done by serious physicists using serious mathematics. It is not the consensus view. It is not the mainstream explanation. But it is on the table, and it has been on the table for some time, and the Hercules-Corona Borealis Great Wall gives it new urgency. So let us approach it carefully. Let us build toward it the way we have built toward everything else tonight, step by step, with each step resting on the one before it. To understand how anything could have begun before the Big Bang, we need to talk about what the Big Bang actually was. And here, the popular conception and the scientific one diverge in ways that matter. The Big Bang was not an explosion. It was not matter being hurled outward from a central point into a pre-existing empty space. It was the beginning of space itself, the beginning of time itself, the initial state from which the observable universe grew. Before the Big Bang, in the conventional model, there was no time. There was no space. There was no before. The Big Bang was not an event in time. It was the beginning of time. This is a difficult thing to hold in the mind. We are accustomed to thinking of events as happening at particular times, in particular places. But the Big Bang did not happen at a time, because there was no time before it. It did not happen in a place, because there was no space before it. It was the coming into existence of the very framework that makes events possible. But that clean, simple picture has been complicated by decades of theoretical physics, by the theory of cosmic inflation, by the mathematics of quantum gravity, by models that extend the story of the universe backward or sideways into territory where the concept of before becomes ambiguous but not meaningless. Cosmic inflation is the theory that the universe, in its very earliest moments, before the hot, dense state that we call the Big Bang proper, underwent a period of exponential expansion. In a tiny fraction of a second, a fraction so small that it makes a billionth of a second look like an eternity. A region of space smaller than a proton expanded to a size larger than the observable universe is today. The numbers involved in inflation are almost violent in their extremity. The universe expanded by a factor of at least 10 to the power of 26 during the inflationary period. That is a number with 26 zeros after it. In less time than we have a name for, the universe became unimaginably larger than it was. This inflation smoothed out any pre-existing irregularities, flattened the geometry of space, and generated the pattern of quantum fluctuations that eventually became the seeds of all cosmic structure. It also, crucially, set the initial conditions for everything that followed. The universe we live in, with its particular distribution of matter, its particular spectrum of density fluctuations, its particular arrangement of the cosmic web, was shaped by inflation. The pattern was set before the hot plasma phase began. Inflation is not a speculative idea. It has made predictions that have been confirmed by observations of the cosmic microwave background. It correctly predicts the flatness of the universe, the fact that its geometry is, as far as we can measure, perfectly Euclidean. It correctly predicts the spectrum of temperature fluctuations in the microwave background, the particular pattern of hot and cold spots that encodes the seeds of all structure. It is part of the standard picture, but inflation raises a question that the standard picture does not fully answer. What caused inflation? What was the inflaton, the field that drove this period of exponential expansion? And what happened before inflation began? These questions push us into territory where physics becomes less certain, where the equations are harder and the observational tests are more indirect and the theoretical possibilities multiply. But the territory is not empty. There are real mathematical frameworks for thinking about it. And some of those frameworks produce possibilities that bear directly on the Great Wall. The mathematics of inflation suggests that once inflation begins, it is generically self-perpetuating. In most regions, inflation ends. The inflaton field decays, and its energy converts into the hot plasma of the Big Bang. But in some regions, quantum fluctuations push the field back up, and inflation continues in those regions even as it ends in others. This process, called eternal inflation, means that inflation, once started, never fully stops. It continues forever, producing new regions of post-inflationary space, new Big Bang regions, each one an enormous universe in its own right, separated from all the others by an ever-growing expanse of still inflating space. In this picture, the multiverse, our observable universe, is one bubble in an infinite sea of bubbles. One region where inflation ended and a hot Big Bang phase began. And the boundaries of our bubble, the edge of what we can see, are not the edges of reality, but the edges of our particular post-inflationary domain. Beyond those boundaries, if eternal inflation is correct, are other domains, other universes, each one potentially with different properties, different densities, different physical constants, different laws of nature. Each one a result of inflation ending under slightly different conditions. And here is where the Great Wall enters the picture in its most radical form. In eternal inflation, the state of the inflaton field at the moment when inflation ends in any particular region determines the initial conditions of the universe that forms there. It determines the distribution of density fluctuations. It determines the spectrum of perturbations that will seed the cosmic web. It determines, in short, what kind of universe will emerge. But the state of the inflaton field at the end of inflation is not independent of what happened before. Before inflation ended in our region, before our Big Bang, the inflaton field was in some particular state, some particular pattern of quantum fluctuations that was itself the result of physics operating in whatever came before. And that prior state, that pre-inflationary pattern, could, in principle, be imprinted in the initial conditions of our universe in ways that only become visible at the very largest scales. The density fluctuations that seed the cosmic web in our universe are, in the standard picture, set by quantum fluctuations during inflation. These fluctuations are predicted to be very nearly Gaussian, very nearly random, with a specific statistical pattern that lambda CDM correctly predicts and observational surveys confirm. But if the inflatant field, before inflation ended in our region, had some coherent structure, some large-scale pattern imprinted by pre-inflationary physics, then the density fluctuations it generated would not be purely random. They would carry the imprint of that pre-existing structure. And that imprint would show up in the universe that formed as anomalously large coherent structures, structures that are more extended and more connected than a purely random distribution would produce. The Hercules-Corona Borealis Great Wall, 10 billion light-years long, too coherent and too large to have formed by the processes we understand, might be exactly such an imprint. Not a structure that formed after the Big Bang, through the slow accumulation of matter under gravity, but a pattern that was already there, encoded in the initial conditions, a fossil of whatever preceded our universe. If this is true, if the Great Wall is a relic of pre-inflationary physics, then it is not just the largest structure in the observable universe. It is the oldest. It predates the Big Bang in the sense that its seeds were set before our hot plasma phase began, before atoms formed, before stars ignited, before any of the familiar physics of the universe had a chance to operate. It would mean that when astronomers look at the Great Wall and detect the gamma-ray bursts of its dying stars, they are looking at the imprint of a process that occurred before the universe they know existed. They are reading the prehistory of reality. They are seeing, encoded in the distribution of matter across 10 billion light-years, the handwriting of whatever physics was at work before our Big Bang. That is a staggering thought, and I want to sit with it for a moment before moving on, because it deserves more than a passing acknowledgement. We are made of atoms. Those atoms were forged in stars. The stars were born in galaxies. The galaxies condensed from density fluctuations. The fluctuations were seeded by inflation. And inflation, in this picture, was not the beginning. It was preceded by something we do not yet fully understand, something that left its mark in the pattern of matter we see today. The chain of causation reaches back before the Big Bang, and the Great Wall, that impossible, anomalous, 10 billion light-year wall of galaxies, may be where that chain becomes visible. There is another possibility in this territory, one that is related but distinct. Some physicists have proposed models in which our universe is not the only post-inflationary bubble, but one of many that interact and collide at their boundaries. In these models, the collision of two bubble universes would leave a distinctive imprint on the cosmic microwave background, a pattern that has been searched for, without definitive success. But such a collision might also leave an imprint in the distribution of matter, a region of enhanced density corresponding to the zone where two bubbles met, a coherent structure at a scale determined not by gravitational collapse within our universe, but by the geometry of the collision between universes. The Hercules-Corona Borealis Great Wall, in this picture, might be the scar of a collision, a region of our universe where another bubble universe pressed against ours, where the boundary between two different post-inflationary domains briefly overlapped, leaving behind a concentration of matter that has persisted ever since as the largest structure in our observable sky. A scar from a collision between universes, 10 billion light-years long. Visible, if you know how to look, in the pattern of gamma-ray bursts detected by a satellite in orbit around our small planet. These ideas, inflation imprints, bubble collisions, pre-Big Bang physics, are at the frontier of theoretical cosmology. They are speculative, in the sense that they have not yet been directly confirmed by observation. But they are not arbitrary speculation. They emerge from the mathematics of inflation, from the equations that already form part of the Standard Model, extended into territory where those equations have not yet been tested. And the Hercules-Corona Borealis Great Wall, too large, too old, too coherent to have formed by the processes we understand, is exactly the kind of observation that those frontier theories might explain. To find a structure that cannot be explained by what happened after the Big Bang is, potentially, to find evidence of what happened before it. And that possibility, that the largest structure in the observable universe is a fossil of the universe's prehistory, is one of the most profound things that science has ever put on the table. Whether it is true, we do not yet know. The observations needed to test it are at the edge of what our current instruments can do. Future surveys, with better sensitivity and larger sky coverage, might find the predicted imprints of pre-inflationary physics in the distribution of matter at the very largest scales. Or they might not. The question is open. But the question is on the table. And it is on the table, in significant part, because of the Hercules-Corona Borealis Great Wall. Because a structure too large to exist forced cosmologists to consider explanations that reach beyond the Standard Model, beyond the age of the universe, beyond the Big Bang itself. Before the Big Bang, the universe was not old enough to build the Great Wall. So perhaps the Great Wall is older than the universe. Let that sentence rest in the silence for a moment. Let it be impossible and possible at the same time. Let it be the thing it is, a question that the data has forced us to take seriously, a question that reaches back before the beginning of everything we know. And let it remind you that the beginning of everything we know is not the beginning of everything. We have come a long way tonight. From the ceiling of your room, to the edge of the solar system, to the Milky Way, to the observable universe, and then beyond, to the Hercules-Corona Borealis Great Wall, 10 billion light-years long, too old for the universe that contains it, possibly older than the Big Bang itself. We have walked through the discovery, the physics, the paradox, the broken principle, the inhabited interior, the failing map, and the possibility that the Great Wall is a fossil of something that predates everything we know. Now we have arrived at the end, and endings, in this kind of journey, are not summaries. They are not places where the loose threads are tied and the questions are answered and the mystery is resolved. They are places where you stop walking and turn around and look at how far you have come, and then look forward at how far there is still to go, and choose to rest for a moment at the edge of both. So let us rest. But before we rest entirely, I want to offer you something. Not a conclusion. I have said we are not doing that. But a reframing. A way of holding everything we have discussed that is less about the impossibility and more about what the impossibility means for us. Here, now, in this quiet moment at the end of the journey. The Hercules-Corona Borealis Great Wall exists. That is the first and most fundamental fact of everything we have discussed. It is not a theory. It is not a mathematical prediction. It is an observation made with real instruments, confirmed with real statistical analysis, replicated with real, independent methods. Something 10 billion light-years long is hanging in the universe, in the direction of two constellations in the night sky, whether we are thinking about it or not. It was there before anyone found it. It was there before NASA launched the Swift telescope. It was there before the first human being looked at the sky and wondered what was in it. It was there before the Earth existed and the Sun existed and the Milky Way had formed into its current shape. It has been there, quietly, enormously, impossibly, for most of the history of the universe. And it will be there long after tonight. Long after this conversation ends and you fall asleep and wake up and go about your life. Long after every human being now alive has lived out their years and been replaced by other human beings who will also live out their years. Long after our civilization has risen and fallen and been replaced by whatever comes after. The Great Wall will still be there. The galaxies within it will still be burning. The stars within those galaxies will still be living their long, slow lives. And the structure itself will still be doing what it has always done, simply existing, at a scale that defies comprehension, in a universe that cannot fully explain it. It exists, and it should not. That is the second fact. By the best models we have, by the physics that has been tested against every other large-scale observation, the Great Wall is too large to have formed in the time available. It is too coherent to exist at the scale where the universe is supposed to be smooth. It breaks the rules in ways that we cannot ignore and cannot yet fully explain. And that breaking of rules is not something to be frightened of. It is something to be grateful for. Because the breaking of rules is how science grows. The breaking of rules is how maps get extended. The breaking of rules is how the next generation of scientists finds the questions that will occupy their careers and define their contributions. The Great Wall is a gift, a 10 billion light-year-long gift from the universe to the curious. And it may be telling us something profound. That is the third fact, or perhaps not quite a fact yet, but a genuine and serious scientific possibility. Something about the very largest scales of the universe, something about the initial conditions set by inflation, something about what existed before the Big Bang, may be written into the structure of this wall. The largest thing we have ever found may be the oldest thing we have ever found, and its age may extend back beyond the beginning of everything we know. Those three things, it exists, it should not, and it may be telling us something profound, are the shape of the Great Wall as we understand it tonight. Not a complete picture, not a solved problem, but a genuine mystery in the best possible sense of that word. A thing that is real and known and measured and still not understood. Let us talk about what it feels like to live in a universe that contains things like this. Not as a thought experiment, as a genuine reflection on what it means to be a conscious being at this particular moment in cosmic history. We are small. There is no other way to say it. Against the scale of the Great Wall, against 10 billion light years of dense cosmic web, we are smaller than a single atom is against the size of the Earth. The comparison is not even close. We are orders of magnitude beyond small. We are a rounding error in the arithmetic of the universe. And yet here we are, aware of the Great Wall, aware of its size, aware of its impossibility, aware of the paradox it represents and the questions it raises and the possibilities it opens. We are the rounding error that knows it is a rounding error. We are the infinitesimal that can calculate its own infinitesimality. We are the tiny things that found the largest thing and named it and measured it and sat with the discomfort of not fully understanding it. That is not nothing. That is, in fact, an extraordinary thing. The universe produced us, among all the possible things it could have produced, and we turned around and found the most anomalous structure it contains. We built the instruments. We analyzed the data. We followed the logic wherever it led, even when it led somewhere that broke our best theories. And we are still following it, still asking the questions, still willing to sit with the discomfort of not yet having the answers. There is a particular quality that the very largest things in the universe have when you allow yourself to feel them rather than just to think about them. They produce a kind of stillness. Not the stillness of nothing happening, but the stillness of something so large and so slow that its motion is imperceptible, like standing on the surface of the earth and feeling, if you are very quiet, very still, the impossibly slow turning of the planet beneath you. The Great Wall is doing something like that right now. Its galaxies are moving, drifting apart as the universe expands, interacting gravitationally, occasionally merging. Its stars are burning, fusing hydrogen into helium, producing energy that radiates out into the space around them. Its planets, if there are planets, are turning and orbiting and experiencing whatever they experience. All of this is happening right now. At this very moment, as you breathe and listen, all of it is happening at a pace so glacial that the entirety of human history would not register as a perceptible change in the structure's arrangement. We are like mayflies trying to comprehend the growth of a mountain. The timescale is simply not one that our biology is equipped to feel. And yet we can know it. We can understand it. We can hold in our minds the fact that the Great Wall is evolving on a timescale of billions of years, even though we will never observe that evolution directly. We can hold in our minds the fact that its stars will burn out and be replaced by new generations, that its galaxies will drift and merge, that the structure itself will continue to change long after every conscious being we know of has ceased to exist. That capacity to know things that operate on timescales and spatial scales so far beyond our direct experience is one of the most remarkable things about being human. We are creatures of the moment, our lives measured in decades, our direct perception limited to the room-sized world immediately around us. And yet we can reach, through mathematics and observation, to 10 billion light years and to the beginning of time. We can find the Great Wall. We can measure it. We can be unsettled by it. So as we close tonight, as the questions settle back into the dark from which they came, let the Great Wall be something you carry with you, not as a weight, but as a presence. A reminder that the universe is stranger than we know, larger than we can see, and older, perhaps, than the Big Bang that we call its beginning. A reminder that the night sky above you, the same sky that humans have looked at for as long as humans have existed, still contains things we have not found, still contains structures we cannot explain, still contains, at its very largest scales, the kind of mystery that keeps science honest and keeps wonder alive. The Hercules-Corona Borealis Great Wall is out there, in the direction of two constellations 10 billion light years away. It has been there for most of the history of the universe. It will be there tomorrow and next year and in a billion years. And it will continue to insist, in its quiet, colossal way, that the universe is not yet fully mapped. That insistence is a gift, one of the largest gifts the universe has given us. And so we come to the very end, not the end of the questions. Those continue, out in the data and the mathematics and the late nights of researchers who are still working on this, still trying to understand what the Great Wall is telling us. But the end of tonight's journey, the end of this particular walk from the familiar to the impossible and back again. Let your body be heavy. Let the surface beneath you hold all of your weight. Let the scale of the Great Wall be present, not as something you need to solve or understand completely, but simply as something that exists. Something real and enormous and ancient, hanging in the universe in the direction of two constellations, requiring nothing from you except the willingness to know it is there. The ceiling above you is the same ceiling it was when we started. The room is the same room. The world outside is going about its business as it was before. But you have been, in the course of this evening, to the edge of the observable universe and found something waiting there that should not be possible. And that trip, that imaginative, mathematical, physics-grounded trip to the edge of what we know, leaves a residue. A slight but permanent adjustment to the sense of how large reality is, and how much of it we do not yet understand, and how much more there is to discover. The universe is not finished with us. We are not finished with the universe. The Great Wall is 10 billion light years of evidence for both of those things. Rest now. Let the scale of things hold you. Let the impossibility of the Great Wall be something soft and vast and present in the dark. And know that the universe, which is stranger than we know and larger than we can see, contains you too. You are 10 billion light years from the wall, and you are here. And both of those things are true and remarkable and worth resting in. Good night.